So, so hello everyone. Welcome to the fifth tutorial of the course Nuclear Astrophysics. So, yeah, good evening. So, okay. So I think, as I told in the last class, that we will start today's class with the topic which I wanted to cover in the last week. So I will start with the shell model and the liquid drop model of nucleus, and I have found some problems related to shell model also in the assignment. So first we will do those two topics, then we will go to our basic nuclear astrophysics course, and then I will solve the assignment problems of week 5. Okay, so these are the problems. So let us first go to the shell model, just a second, and the liquid drop. Okay. Yes. Yeah, yes. I have not found that book. I think the PDF copy is not available. So one thing I can do, yeah, so one thing I can do, I have not checked it in my institute library. If I found the book in the library, then what I will do, I will take the photo of those pages which are needed for that particular problem, or that course. Then I will share those photos with you. Okay, so that I will try to do in the next week. This week I could not get that book. I have tried to find it. Okay. Yeah. Okay. Okay, so let us start with the liquid drop model at first. You know that there are mainly two models of nucleus. One is liquid drop and other is shell model. So liquid drop is the simplest model of the two, in which the assumption is that the nucleus, it will behave like a drop of a liquid, I mean drop of a rain, you can think of it. That means it is a solid liquid drop type thing, the nucleus, and the nucleus are inside the nucleus. So this type of crude understanding, you can say it as a crude model of nuclear, sorry for that, crude model of the nucleus. So if you consider this particular model, the main important thing is, using this model we can express our the binding energy in terms of, so binding energy Be, which is the energy that is responsible to confine the nucleons inside the nucleus, that can be written down by, at first I will write, so AC Z, Z minus 1, A 1/3, AN, A minus 2Z, A 1/3 plus minus delta 354. Okay, so this is the expression by which we express the binding energy for this liquid drop model. Now this term is called the surface term. This is asymmetry term. I will come to these terms. So I think I can 9 8 is good. Yes. Now A minus 2n is actually what is sorry. So this was the asymmetric term. Yes, A minus 2z is there. Term. The second one is Coulomb energy, and I will come to the last term at last. Okay, so one thing, just focus that for the first term, which is the volume energy term. So first is volume, second is surface, then the Coulomb energy, then the asymmetric term, and there is an additional term delta by A to the power 3/4, that I will come later. So one thing you can see that the first term is positive, but all the other term, the sign before the other terms are negative. So here it is negative, here it is negative, and it is negative. That means it is like you are subtracting some quantity from the first quantity, which is the volume term. Okay, so that's why the later term, which is the second one, the third one, and the fourth one, we called it as a correction term. So this is coming due to the correction of the of what I will tell you. So, these are correction term, and we are correcting our binding energy, that is why it is coming out to be negative. So, that is the negative reason behind the negative sign of the 4 terms and the positive sign of the first term. So, the main term which is responsible for the binding energy is this AVV term, okay, which is the volume term. Now, what this term says that generally if you have suppose a proton which has a single nucleon, then you go to helium which has 2 proton, 2 neutron, then you go to the higher and higher order nucleus. So, when you go to higher and higher a number nucleus, that means the number of nucleon is increasing, as well as all the nucleons are either proton or neutron, that means the radius of proton and neutron are fixed. That means with increasing a, the volume of the nucleus will be larger. Okay, that is why the first term is actually proportional to the volume, and as you know that the nuclear density is roughly a constant type, constant value, roughly we can say. So, the mass of a nucleus actually proportional to the volume of a nucleus. More volume means more mass, because the density is constant, and volume is actually 4/3 r cube, 4/3 pi r cube, where r is the radius of the nucleus. So, you can write volume of nucleus is proportional to r cube. Okay, and you know that r is proportional to a to the power 1/3, right? This we have already done. So, if you put it here, it will be proportional to a. That means your volume of nucleus is proportional to a, as I told you that with increasing number of a, that means nucleon, the volume will be increasing. So, that is why the first term is actually proportional to this volume. So, it is proportional to volume, and if I want to convert the proportional sign to a equals to sign, then I have to add a constant. This is the constant, this is the constant coming into the volume term. So, AV is constant. Similarly, in the second term AS, in the third term AC, AN, all these values are constant. Okay. So, this is the reason behind the volume term, which is the main factor of the binding energy. Now, we will come to the correction. So, why the surface correction term is coming? Now, as you know that if it is a nucleus, there are nucleon inside. So, I will change. So, suppose this particular nucleon which is in blue, it has surrounding nucleons also inside the nucleus, right? But if there is a nucleon which is at the surface of the nucleus, for that it will not, it do not have any nucleus outside of its radius, right? So, it has nucleus here, the surrounding nucleons are here, but there is no nucleus in this particular location. So, it is not covered wholly, I mean fully, by other nucleons. So, that is why the surface correction terms comes into the picture, because now we have to subtract some energy which we have already considered in the volume term, because of this asymmetry. I mean, not exactly not this asymmetry, don't confuse with this asymmetry term. This asymmetry is due to the positioning of the nucleons inside the nucleus. Okay, so that is why this term comes into the picture. I will not go into very deep details. So, that volume term BS, the surface correction term, is actually proportional to the surface area of the nucleus, that means r square, and as r is proportional to a to the power 2/3, we can write it a to the power 1/3. So, we can write it a to the power 2/3. So, we are trying to express all the terms, not expression, terms in terms of atomic number, because that is the most fundamental thing, and that we know for different nuclei. Okay. So, your BS, the surface term will be proportional to a to the power 2/3, and again if you convert it to a value, then it will be as to the power 2/3, that as is the constant. Okay, so, this is the reason behind the surface term, the asymmetry of positioning of the nucleons. It is solely coming for the nucleons at the circumference of the nucleus. Now, coming to the Coulomb energy. So, you know, suppose let us consider this nucleus again. So, if there is a nucleon inside the nucleus, and there are several other nucleons around it. So this particular nucleus, which I have denoted by the blue circle, it will feel the Coulomb repulsion due to the other protons. Why I am using proton? Because precisely proton will take part in this Coulomb repulsion, because neutron don't have any charge. So proton interaction will be there inside the nucleus itself, and that repulsion. So binding energy is attractive force, and the Coulomb energy is the repulsive force. So it is obvious that we have to subtract that repulsive force from the repulsive energy from the binding energy. So that is the reason behind the minus sign in front of the Coulomb energy. We are subtracting this contribution from the total binding energy because it is repulsive. Okay, and so if the number, I mean the proton number, if the proton number is Z, where A is actually Z plus N, where Z is the proton number and N is the neutron number. Sorry. So if the proton number is Z, then okay, then this energy will be proportional to the, I mean it, okay, so I will do this in this way. So suppose that blue nucleons is here, I am just drawing this thing, it is here, other nucleons are there. So it will feel repulsive force due to this particular nucleons, then again this, so it will feel the repulsive force, the Coulomb energy force due to all other existing protons. So now if there are Z protons, any interaction can be happened between two particular protons. Okay, this particular proton can also feel the repulsive energy force due to this one, again this one, this, I mean the force will act in a pair of neutron. Now if a pair of proton, now if you have Z number of protons, and if the force is acting between any two proton, then you can select your two proton from that Z number of protons like ZC2. It is a mathematical expression, I don't know whether you know it or not. It is coming from the permutation combination chapter of the mathematics. This is basic mathematics. So suppose you have Z number of particles, you want to take two particles from that, then you can select them as ZC2, and if you express it, it will be Z into Z minus 1 by 2. Okay, so yeah, Z into Z minus 1 by 2. That means this number of pairing can be formed inside a nucleus which has Z number of protons, and this is the number of pairing. Now for the energy we have to divide it by the R also, because you know that for any two particle, if it has Z1 energy, Z2 energy, that is Z1 Z2 square divided by R. It is generally the Coulomb repulsion, Coulomb force or Coulomb energy due to Coulomb energy, not force. Force will be R square. So it is energy due to two protons, between two protons. Now that's why there will be here also radius, a factor of radius will come into the picture. That's why we will write this term, this Coulomb energy term, as proportional to this Coulomb energy term. Suppose Coulomb proportional to Z into Z minus 1, that is number of combination, divided by R, that is the radius of the nucleus, and again we can write it R a to the power 1 by third. So this is proportional to Z times Z minus 1 by a to the power 1 by third. So the in the denominator, the a to the power 1 by third is coming from the radius, and the Z into Z minus 1 is coming from the number of combination in how many ways you can select two protons from the Z number of protons. Okay, so that's why you can see this term, this Coulomb energy term, the third term, this one is Z into Z minus 1 by a to the power 1 by third, and another constant AC is there. So AC, AS, AV, all these terms are constant. So this was the due to Coulomb energy. Now there comes the fourth term, which is the asymmetric term. So asymmetric term, pardon me if I am my spelling is wrong, maybe. So asymmetric term. So why this comes into the binding energy calculation? Because so for helium we have two protons, two neutrons. For oxygen also we have 8 protons, 8 neutrons. So you can see we have as much number of protons, we have same number of protons and neutrons. So this thing, this I mean equal division of protons and neutrons happens up to some mass number of element. But if you go to higher and higher order elements, then you can find that the neutron number is much greater than the proton numbers. So for this type of elements, n is equivalent to z. But for higher elements, like for iron only, iron, you can, if you see it, iron is actually the stable one, 26 Fe56. Correct me if I am wrong. So that means you this protons has 26 number of protons and neutron has 30 number of neutrons. Okay, so neutron number is greater than proton, so you can write it as z. So this is the reason behind the asymmetric term. When we are going to higher and higher order elements, the number of neutron is greater than the number of protons, and the symmetry is breaking. Symmetry has been broken. Symmetry means n is equals to z. So that's why the asymmetric term comes into the liquid drop model. Now the neutron excess, that means how many number of neutrons are greater than the number of protons, that is n minus z. And so your this term, that Bn, that is the energy correction due to the asymmetric term, I am writing as Bn, it will be proportional to this neutron excess, and it will also be proportional to the excess volume which is taken by this excess number of neutrons. So it is also proportional to the volume n minus z by a. If your total volume is proportional to a, then the volume which the excess neutron is taking, that is n minus z by a actually. Okay, so these two holds only if it is proportional to both of them. That means n minus z square, n minus z square by a. Okay, and I have written here that a equals to z plus n. That means n can be written as a minus z. So if we write n as that, so it will be a minus 2z square by a. So we are trying to express, as I told you, everything in terms of mass number. So the proton number is substituted by the mass number minus neutron number. The neutron number has been substituted by the mass number minus the proton number. So that's why a minus 2z whole square divided by a term will be there. If I go back to the asymmetric term, you can see here that a minus 2z by a minus 2z by a will be there. So I think I have written it wrong. Yeah, it is a, sorry. So a minus 2z by a term will be there, and that an is the constant related to this particular term. Now coming to that, so all these three the surface, the Coulomb, and the asymmetric term was correction of the binding energy. Now coming to the fourth term, that is delta by delta by a to the power 3/4. So this is actually is coming due to the stability of the nucleus. This term comes due to the stability of the nucleus, because that suppose there are certain case can happen that your z, a, and n, right, these three, neutron plus proton is equals to z. Now this can be odd, this can be odd, and this can be even. Similarly, this can be even, this can be even, and this will be even. And other combination is also possible, odd, even, that will be odd. Similarly, even, odd, that will be odd. Okay, so it has been found by the researcher or by experiment that when this odd term is just a second, I will check it whether I am telling it right or not. Where is that? Yes. So when the term is when that z is even, n is also even, that means this particular thing, Yes, even highly stable, because you will see that the nucleons also have spin, one up spin, one down spin. Now if you have even number of neutrons or even number of protons, that means all the particles are paired. So one positive spin will be paired with the negative spin. So all the particles are paired and there is no excess of neutrons or protons. That's why this even term is most highly stable. This is the most stable. Okay, and for this particular configuration, the value will be minus delta by a to the power 3 by 4. Okay, and if you have odd numbers of protons, odd numbers of neutrons, so after pairing, suppose you have 27 number of protons, so 26 proton will be paired in 13 pair, but there will be a single proton, which will remain unpaired. Similarly, for odd neutron case also, there will be a single neutron which will be unpaired. So that's why it will decrease the stability of the nucleus, and it is the least stable. It is the least stable configuration. Okay, so for the least stable configuration, that value will be delta by a to the power 3 by 4. Okay, so you have to consider, I mean you have to know the proton numbers and neutron numbers to add or subtract the last term, which is plus, it can be plus and minus depending on the number of n and z, and these two are the intermediate. It is the not most stable, not least stable, it is intermediately stable, and for this configuration the value of the last term will be 0. So the last term will depend on the proton number and neutron number. So it is if it is this configuration, then there will be no term like this. Okay, that's why I treated this term separately, because exactly it is not coming into every calculation of binding energy. Depending upon the nucleus or property of the nucleus, I mean the number, it will be there or it cannot be there. Okay, so these were the main terms. So this is the liquid drop model general understanding, and what type of problem you can see from this liquid drop model, that it can be asked that if you have a liquid drop model, you have been given the proton number, the neutron number, everything is given, and you can be asked that what is the most stable configuration of that particular nucleus. So what you will have to do, that you have to ddz of B E, that is binding energy, because binding energy is a function of Z. Okay, so ddz of binding energy equals to 0. By doing that, you can find the number of Z for which the nucleus will be more stable. I mean, in that problem you will be given the A, the N and Z separately it will not be given, the A will be given. All the values of this AB, AS, AC, AN, everything will be given. Then you can express your binding energy as a function of Z and just differentiate that with respect to Z equals to 0, and that will give you the number of Z for which the particle will be stable. And if you can get the number of Z, just just subtract it from the A, you will get the N. So this type of problems generally comes into exam. I mean, this is the most repeated or most important problem from the liquid drop model. So I will not do that problem because it is not there in the assignment. If there is any problem in the later assignment, I will do that. Okay, now this was the general understanding. If you have any question, you can ask. Yes, yeah, the binding energy of nucleon is positive value. Yes, uh, okay, even and even delta should be achieved. Yeah, this is a good question. I will look into it. Right now I will not give any answer because it may be wrong. I will think. I mean, today also during taking the class, I will think what will be the negative. Yes, I can understand that volume term is positive. That is the main important term of the binding energy. And all those are correction, which are subtracting from that particular first term, right? You want. There will be a positive. But I have taken it from the book only, and I can say that what I have written is right till now, because here it is written even is minus and odd is plus. So I will look into it. Okay, I will let you know. So pairing option. Just a second. Oh, so BP this is mentioned. Yes, I will look into it. I will tell you next class, or if possible, I will tell you at the last of today's class only. I will go through the a small section of a particular book. Okay. Yeah. Okay. Now coming to the cell model. So cell model is actually a better understanding of nucleons, and there are many other things or other properties which cannot be explained by this crude model of liquid drop. That's why the cell model comes into the picture. So what the cell model tells actually, so what we are considering that our nucleus, this is, if this is a nucleus, and in the liquid drop model we have considered that it is a solid body and it acts like a drop of a rain or drop of a water, whatever you can say, liquid, drop of a liquid. Now in the cell model the assumption is that that each nucleon, that I mean there are many nucleon, right? So suppose if you consider one particular nucleon, this nucleon is actually experiencing the force due to other nucleons, okay, and it moves inside the nucleons only, that it moves independently. This is the assumption that this one particular nucleus moves inside the one particular nucleon moves inside the nucleus irrespective of the others. And if you assume this particular configuration, then the understanding is that this one single nucleon moves, I will write it independent from book, directly from book, because it is important. So one single nucleon moves independently of others in the time averaged field of the remaining nucleons. So this is the important line, that's why I written is. So the assumption is that one single nucleon moves independently of others. This is only possible if you consider the time averaged field. This term is important. So time averaged field of the remaining nucleons. Under this assumption only you can write the Schrodinger equation for a particular nucleons inside a nucleus, and it has been shown that if this condition, this assumption is taken, then you can write your Schrodinger equation h square by 2m gas square plus half k r square psi is E psi. This is the Schrodinger equation for a nucleon, where the potential term, so this is the potential term Vr, which we are taking as a time average potential for this particular cell model. Just a second. So that can be written as half k r square. Okay, so Vr can be written as half k r square only under this assumption, which is actually a simple harmonic oscillator potential. So this can be written. This I am telling you as a statement, but this can be shown. Okay, so if you consider this particular time average field, the very simplistic assumption, then you can write the Vr, otherwise you cannot write the Vr. I have told you in the previous tutorials also that there are only few examples we have for the form of the potential which can be solved analytically. All the other forms of potential, I mean 98% of the potential form of the potential cannot be solved by hand. It can be solved by numerically, but this half k r square SHO, simple harmonic oscillator potential, can be solved, and the energy can be written as n plus half h cut omega, where n tells you, n is actually a have value of 0, 1, 2, 3. So in the simple harmonic oscillator, you know that the lowest test has half h cut omega energy, then that will be 3 by 2 h cut omega energy, this type of thing, depending on the value. If n equals to 0, that means half, n equals to 1, that means 3 by 2 h cut w omega energy. So this type of, I mean, understanding can also be applicable for the for that particular single nucleon which is inside the time averaged field of the other remaining nucleons. And for the, I mean, we are comparing, like in the resonant reaction, we have compared it with the damped oscillator, and we have written some expression by comparing the resonant reaction with the damped oscillator. Same thing here, we are comparing our this type of situation with the simple harmonic oscillator, and by that analogy we are coming up with some, I mean, theoretical understanding. Okay, so this n was the number of the simple harmonic oscillator. Similarly, analogically, you can say for our nucleons, there will be some quantum numbers associated, that will be L, which is the angular momentum. There will be S, spin angular momentum. Okay, so these are not exactly same as the values of L, S, N for the electrons, because that is considering an atom, and in the atom consideration we have a strong force of center at the nucleus, but here we are inside the nucleus. So this is quite different from the atomic energy level, but you can draw an analogy between that atomic energy level and the nucleon energy level also. So the more final understanding is similar to the electron, the nucleons inside the nucleus will also have discrete energy levels, which can be written by N, L, S. Okay, so that is the main understanding. This N is associated with this N, which is from the harmonic associated, not analogically, this is associated with the capital N, which was in the simple harmonic oscillator. And if you have L value, so for N there will be 0 to n minus 1 value of L, similarly to the electrons, and S can be calculated by J equals to, so J is the combined momentum number, L plus S and L minus S. Okay, so that you can do. Now yes, just a second. Yeah, so J is called J is the vector addition of the angular momentum L and the spin S. So JH is actually LH plus SH. All these are vector. You know that angular moment and the quantum numbers are vectors in this formalism. So J can be written as this. Now we have J, L, S, N, everything, and we can write the state of a particular nucleon as like this. So your N, and it will be like L, and it will be J, right? If I am wrong, just tell me. I have also forgotten this. Let me check. I could not make note of this particular cell model here, so I think it is right. It can be written like this. So suppose you have N equals to 1, L equals to 0, J equals to, then and S equals to half. Okay, then your J will be L plus half. Yes, just to show, J has only one value have. Yes, S and L. So J, suppose it is half. Okay, 0 plus half equals to half. Then you can express that particular state of the nucleons as 1, and for L equals to 0 we use the S. So you know that S, P, D, F, this we will use 0, 1, 2, 3. Okay, so 1 S, and your J value is half. Okay, so this is the state of the nucleons. Now the second question is, there will be how many number of nucleons in this particular state. So that can be calculated by 2J plus 1. So for this particular state, J is half plus 1, that means 2. Okay, so 2 nucleons will be there in that particular state, 1s half. That's why we will express the total thing like this. 1s half is the state, and 2 says you the number of nucleons. Okay, so this is how we generally express the state of the nucleons inside a nucleus by calculating the NLJ values. Now, and S, this value of S is actually half always. The value of S is half, and actually it is half and minus half. So you can think of as a mod value of half, and while calculating the J, we will one use plus, and secondly we will use minus. So plus minus will be come from that expression. So otherwise you can think of S equals to plus minus half, and J is equals to L plus S only. Then your plus and minus will be accommodated accordingly. Whatever you can think, that is no problem with that, but it is the way. Okay, so now what is so we have different energy levels of nucleons. Now the question is, which levels have higher energy than the other levels? So this can be also calculated, but I will not do it. I will just write something that 1s half, and it is very useful if you can remember the states for at least first 40 nucleon number. Okay, that is very useful. So if your 1s half, then will be 1p 3 by 2. So 1p 3 by 2 means for this particular state your L is 1, because p correspond to 1, your n is 1, and your J is 1 plus half, that is 3 by 2. Okay. So this is that state. Similarly, there will be a 1p half state also, because I told you J is L plus minus S, that means L plus half. So 1 plus half will give you 3 by 2, and 1 minus half will give you 1 by 2. So two values of J will be there for this particular configuration. So 1p 3 by 2, then 1p half, then 1d 5 by 2, 2s. So you can see here we have come to 2, that means n, the number of n quantum number has changed to 2. So 2s half, 1d 3 by 2, and others. So in this way you can write, you can go to any of the books I have written here also, just that this is the 1s half is the lowest energy, 1p 3 by 2, then 1p half, 1d 5 by 2, 2s half, 1d 3 by 2. And if possible, just try to remember up to this. So up to this 50, because it is very useful for the exam. Just try to remember it a few times, it will be, because there you can find some pattern. Okay, so like for the lowest, 1s half is the lowest. If you are going just above 1s 1p with higher J number, the energy will be lower. So 1p 3 by 2 will be lower, 1p half will be higher. Again, if you go to higher level, you can make some arrangements according to your understanding, and you can remember. This is all I am telling to remember, how to remember this particular thing. Now this was the energy levels, and as I told you, each energy level has number of nucleons 2j plus 1. So for it will be 2, for p it will be 4, and it will be 2, then again it will be 6, 2, 4. So this type of calculation you can do, and so it is the cell model understanding that nucleons have different. So you can see these states are analogically same as the similar, not same, similar as the state of electrons, because electrons have n, L, J, everything. They are also we have different type of state, but remember this is nucleon state, not electron state. Okay, now so just a second, yes, so this is done, total number of p or n. Now one problem I will do it from, two problem I will do. So suppose you have been given, let me do it just side of this plot or figure. Okay, so we have to calculate the spin and parity of so parity I will come while doing the problem, 27 13 Al. So suppose it is given, and you have to calculate what will be the ground spin state and the parity state. Okay, so 27 Al aluminum, it has 13 protons and it has 14 neutrons. Okay. So here also you can see 27 aluminum also don't follow the symmetry of the proton numbers and neutron numbers. It is slightly broken because one excess neutron is there. So 13p, for this 13p, if we follow this particular configuration, it can be written as, first write the states. So this is 3, okay. 1p half, 1d 5/2 and 1d 5/2s half, 2s half. Just write few states. So this has 2 electrons because 2j plus 1, electrons, protons. So this has 4, this has 2, so 2 plus 4 plus 2, so we have used 8, we have 13, and here the maximum number is 5, so that is 6, right? So this energy state can accommodate 6 number of nucleons, but we are left with 5 only because 8 we have used and the total is 13, so there will be 5 protons here, and there will be 0. All the other high energy terms will not be there for this particular thing. And for 14 neutron also, so you have to calculate for both protons and neutrons, 1p half, 1d 5/2. Okay, similarly this will be 2, 4, 2 and 6, right? Now you can see that for neutron, this energy level is already populated, I mean fully populated. Now when you have to calculate the spin, at first you have to find out how many unpaired protons or neutrons are there. So in this particular problem there are no unpaired neutrons because here 6 is filled, this 2, this 4 and this 2, all the states are filled. But here if you consider this particular state 1d 5/2 to the power 5, there is 5 protons. In that 5 protons, 4 protons will make 2 pair with plus spin, with minus spin, with plus spin, with minus spin. So 4 protons are there, they have making 2 pair, and there is one single proton which is unpaired proton. So this is unpaired and it has only one spin. Suppose it has only spin half. So you have to find out which is the where the location of the unpaired nucleons inside the nucleus, and the value corresponding to that the value of J corresponding to that unpaired nucleus. For our case it is 5/2. Okay, so this is the value of J for this particular nucleus, and as we have gone up to D, that means L equals to D because SPD 0, 1, 2. Okay, so L is equals to 2 for this state. It is the final configuration of the nucleus. And if you calculate the parity, so parity will be minus 1 to the power L, that means minus 1 square, that is plus 1. Plus 1 means even parity. Okay, so in exam you have been asked, you may be asked to calculate the parity of a particular nucleus and also these values J, L. You have to only consider the last unpaired electron. Sorry, I am repeatedly saying electrons, so pardon me for that, not electrons. So number of unpaired protons or neutrons there in that particular configuration, that you have to find out. Okay, so here we have one unpaired protons. Now let us do one problem which has one unpaired neutrons also. So I have told you, you have to calculate both the protons and neutrons. Okay, so let us take this one, 33s16. Okay, this has 16 proton, 17 neutrons, and if you express it similar like the previous thing and previous way, so 1s half it will be 2, 1p 3/2 it will be 4, so 4 plus 2 6 we have used, we have 4 more, 10 more, 1p half that is 2, 1d 5/2, just calculate while doing it, 2 plus 4 plus 4, 8 we have taken, we have 8 remaining, so it will be filled, 6 will be there, and the 2s half, 2 are remaining, that will be 2. Okay, and the 17 neutron it will be also same, the first will be same like this 2s half will be full filled square, and so I will write it in the next line, 2s half, so this will be there, and there will be one more neutron because it is 17, 1. Okay, so here you can see all the states are fully filled, 2 4 2 6 2, which is the higher capacity, which is the maximum capacity of each states. But here there is one unpaired electron, because the capacity of this particular thing is 4. Okay. Oh, so sorry, what I have done. So 4. So it is not fully filled, right? Because we have only one electron, one neutron, and that one neutron is unpaired neutron, because it don't have any other neutrons to do pairing. So that unpaired neutron is there. So the value of J for this particular case is 3 by 2. The value of L is SPD, D corresponding to L equals to 2 again, and the parity will be minus 1 to the power L, that is minus 1 square, that is plus 1, again even parity. Similarly, you can sometimes you will find odd parity, no problem with that. But this is the method of doing this type of problem. First, write your configuration of nucleons for protons and neutrons, and then fill all those energy state with numbers, and at the same time calculate how many numbers are left with you, and I mean fill them with accordingly, and find the unpaired electrons. Okay. So this is the you can find a problem. I have not taken a particular that problem from the assignment, but this is the method of doing that. Okay, that I can say. So this was the understanding of cell model and liquid drop model. This was, I should have done it earlier, but I think fine, it is okay. Okay, so if you have any problem here, or you want me to do any other thing, like Sam to ask me that delta problem, I will find it. But if you have any that type of problem, you can also ask, or you can mail me also if you have any problem any day of the week, no problem. Okay, I will try to give you a reply, because right now I cannot reply you, because I am also studying the nuclear astrophysics with you guys, because I have done it much earlier, 3 years or 3.5 years ago. So I have forgotten many of the things. I have to brush up my knowledge also. That's why I cannot tell you exactly at the same time. And you know, while doing PhD or anything, your knowledge comes to a very short short volume. Okay, so I will try to tell address all of your questions if possible. Okay, so this is done now. Okay, so very quickly I will go through the resonant reaction, because we need it for a particular problem very quickly, because you have studied it well in the SARS class. Because I have gone through the assignments. These assignments are mainly the mathematics of the mathematical problems of these assignments are mainly from the older course, because in 5th week course there are nuclear burning, burning of fuel. So from there you cannot find much mathematical questions. Okay, so that's why the assignment is not so important for this week, I mean in the calculation point of view, but the understanding of the theory is important. I will quickly go through it, then we will do the assignments, and then we will end the class. Okay, so yeah, so last day, just very quick, here I have it. Yeah, so last day we did the non-resonant part. Okay, so non-resonant part we have done that our sigma v is 8 by pi mu 1 by kt 3 by 2 e. This is important. Okay, e by kt de. This was our sigma v, I mean mean sigma v, you can say. And here we have used that understanding of sigma b, which can be written as s e by e times e to the power minus b by root over e, or this term can be also written as e to the power minus 2 pi eta, which has been used by Sir. So if we use that particular thing, it will be like this, and from that we have calculated the gamma factor, everything in the last class. So here the understanding is that just a second. Here the understanding is that our sigma, the cross section, varies with the energy. I mean whatever the plot will be, but it is a continuous function of energy, smooth function of energy. and then we have found that at some point, so if it is a Maxwell distribution, if it is a e to the power minus b by root e, then there will be a gamma peak at the intermediate distance, which is the main energy range responsible for the reaction that we have done, the non-resonant part. And we have found that E0, which is the gamma peak, width of this peak by considering the roughly Gaussian form of that gamma peak. All that we have done, and I will not write again, just for a overview. So the width we have written as delta, so it is better to use the notation which we have already used. And this all thing we have done. Also we have seen the dependence of sigma v on the temperature, that depends on tau square e to the power minus tau. So and from this you know that this tau is 30 by kT. It was all in the steps of the calculation, and from here we can write the temperature dependence as T to the power tau minus 2 by 3. So if you can calculate the tau, you can tell the temperature dependence of the mean sigma v. So this was all for the non-resonant reaction. Now the main point is, remember that for non-resonant reaction our sigma was a smooth function of energy, but for resonant reaction, as you know already, this is just a brush up of things, that this sigma is not a smooth function of energy. So if it is energy, if it is sigma, for non-resonant it was like it. Just for the sake of saying, I am telling that a simple smooth function. But now the sigma which can be like this. I mean, for a particular value of energy, which is this value, the sigma is abruptly high. So it is like a delta function, roughly. And for other values of E, like for these values of E, the sigma is completely negligible. Okay. So this is the understanding of resonant reaction. So that's why we have divided our reaction into two class depending upon the dependence of sigma upon the energy. Okay, and you have already studied this resonant reaction is a two-step reaction. So like this, that a projectile will come, it will interact, this is a target, it will interact with the target only if the energy of the projectile lies within this range. I mean, yes, and then it will emit a gamma ray. First it will create an excited state of the compound nucleus, and then there will be a gamma radiation, gamma decay, and the excited nucleus will come to a ground state of nucleus. Okay, that is the understanding of resonant reaction. So it is a two-step reaction, whereas for our non-resonant reaction it was a one-step reaction. So and for the two-step reaction, the sigma gamma, which is sigma is the cross section, gamma I am writing because I am considering that that this equation, this type of reaction which I told you that at the last second part the gamma radiation will be there as tau A by tau B. So this was the partial width, this is tau A, suppose the first reaction of making the compound nucleus, and this is the tau B, the mechanism of emitting a gamma ray radiation. So if it is tau A and tau B, then the sigma gamma is proportional to tau A and tau B, where tau A and tau B are partial width of each step of the reactions. This you have done. Okay, so tau A can be told as formation width, it is formation of the nucleus, and tau B is the decay width because it is the decaying of the nucleus, that means the emission of the gamma. So this you have done, and the main and one important difference, I will say difference from the resonance and non-resonant reaction is, like as I told you that sigma is the major difference, sigma is not a smooth function for this case, and here the quantum number, the angular quantum number for this resonant reaction is very important, because if a particle is going towards another particle like this, suppose it is not going directly, if it is going like this, so it is the impact parameter which has been told by Sir also, and this target, it will this particle, this A, and if it is B, so this A while going towards B, it will look B like this. So for that particle A, the B will be like this. I mean, it is going towards that B, and it depends on the angular number momentum L, how the interaction will happen. because the sigma L, I am writing it max, will be pi of B L plus 1 square minus pi of B L square. Okay, so from where it is coming, actually the orbital angular momentum which is involved in this reaction, that is L h cut, sorry, it is h cut k. It is the momentum, not orbital momentum. This is the momentum for any particle, because in the Schrodinger picture, which is h by k, and it can be written as h cut by lambda cut also. Okay, this is the expression. And if your impact parameter is B, then your L can be written as BP, where L is the angular momentum, and it can be written as B h cut by lambda. So this is just a brush up of things which I have already done. So that is the reason, so B, so fine, this is we got. And from the nuclear point of view, that angular momentum is always can be expressed by the LH cut, right? This is the angular momentum, LH cut. When I have done that cell model, there I also add up the angular momentum vector and the spin momentum vector, which was LH cut and SH cut, right? So that is the angular momentum. Now h cut will be cancelled out, and your B will be L lambda. So the impact parameter, that depends on the angular momentum of the particle and the wavelength of the particle. So it will be L lambda bar. That's why this zone that particle will see when it is approaching the particle A will see when approaching towards the B, that it is different for different values of L. Okay. So from there it is coming, and for a particular value of L, it will see the ring, I mean ring like structure, which is the area between L plus 1 and L, that is the cross section. So this is the understanding actually, 2L plus 1. So sir have done it in a very good way. I am just giving you a rough idea. Again I am telling you. So this can be written down. So this is another major difference from the resonance non-resonant reaction. Here we have not considered anything like L or this angular quantum number. So okay, so if you consider L, and similarly if your one angular quantum number is associated, there will be another, that is capital, that is S will be also there. So spin, which is spin. Now the total factor can be written as a combination of both. So J is again L plus minus S. So J quantum number is important every time. So 2J1 plus 1, 2J2 plus 1. Okay, so this we can, I mean this is the thing which we write as W. This is the expression, and all this thing I am trying to tell you that ultimately the sigma E for this for this resonant reaction can be written down as pi lambda square is the maximum thing, then the statistical factor which is coming solely due to the dependency of L, what I told you here on the impact parameter, and this 1 plus delta by 2 will be there, that is due to the, I mean if it is the same particle, then delta 1 2 will be 1, and it will give you a value of 1, the delta. And the tau A, tau B, it was there, and E minus ER. So this is important. This is actually coming from the analogy of the damped oscillator, which cannot be shown here. So this term is coming from that particular thing, where ER is your resonant energy. So in the non-resonant case, we have the gamma peak E0. So E0 and what role of E0 is in the non-resonant reaction, the same role is carried by the ER in this resonant reaction, where it is the resonance energy. So it is written like this, and it is called the Brit-Wiener formula. Okay. Now for the non-resonant thing, we have written SE by E, e to the power minus B by root over E. Just compare these two. This is for non-resonant and this is for non-resonant. So our main target was to express the sigma in terms of energy, which we have done. And as we have the mother formula, I will say the mother formula sigma V, according to our reaction, whether it is resonance or non-resonance, we will put the sigma E. If it is non-resonance, then we will put the expression with the S factor, and if it is resonance, we will put the Breit-Wiener formula which I have just expressed the sigma e. This is the understanding. Now, by this we generally do the resonance reaction, resonance reaction. So, this is the very brief overview, and if you go through the other things also, so it is the picture of the cross section of I mean not cross section here, many multiple things has been plotted. So, the probability, so Maxwell-Boltzmann distribution has been shown by this curve, and the narrow resonance for which the partial width is very less than the resonance reaction, resonance energy. If this if we consider this energy, so this is the peak, I mean this is the range in which the reaction will occur. If your E of the projectile lies between this range, I mean this range, then the reaction will occur. If your E is like this value, it will not occur. Here also it will not occur. It is not a smooth function. Okay. So, this was the point, and so if you calculate the, I mean if you put that Breit-Wiener formula in that mother equation of mean sigma v, you will end up with the expression. I will not do, just go through the class, that is 2 pi mu kt 3 by 2 h car square omega gamma. It has been also done. Okay. Er by kt f is the skinning factor due to the other electrons. So, and here one extra term gamma I have written, it is gamma, as far as I remember, it is tau a tau b by tau, right? That was the gamma factor I have written, yeah, tau a tau b. So, gamma a gamma b, I am telling it tau, I have some this type of problems. Okay, tau. So, this is gamma a gamma b. So, if I have told this as tau, just pardon me, it is gamma, capital gamma actually, gamma a gamma b by gamma, which is called the strength of resonance. So, these are the important factor of resonant reaction, strength of resonance. Okay. Okay. Now, this is the rough idea. I will not go into details because it is already very detailed. And okay. So, we will now go to the problems. Then if needed, I will come to the theory part again. So, not theory part, the brushing up of the theory. So, I have gone through the 5 and assignment number 5, and it is a very, I mean very easy assignment. You can do it from the previous knowledge of the previous weeks also. You don't have to understand any new thing, because what is the minimum temperature, and I have shown the, I have seen the assignments which Sam sent me, and now those assignments are more or less same. I mean the assignments which I have from the previous year's course, and which you have got for this current year course. So, almost they are same now, right now. Okay. Now, what is the minimum temperature required for the fusion of two protons classically? So, this was the problem of assignment 5. So, if it is easy problem, then it is my duty to go through those problems because I cannot oversee that. So, what is the minimum temperature required for the fusion of two protons classically? So, how I will calculate it? Can any one of you tell me just the procedure, how to do it, which step and which step, which after which, if you are interested. Okay, so what we will do, we will just first calculate the Coulomb barrier Vc, or the Coulomb potential, and we will equate the Coulomb potential or energy with the thermal energy. Then we will find the temperature which is required to break that Coulomb barrier, to overcome the Coulomb barrier. So, Vc is Z1 Z2 square by R, as you know, and Z1 and Z2 is 1 for our case, and E square you can write it 1.44 into 10 to the power minus 10. Okay, in terms of kV by 7, and it will be R will be again R0 a to the power 1 by third plus A1 A2 1 by third, and for two protons A1 A2 all are 1, and R0 asked you to remember, I told you to remember it 10 to the power minus 13, yes, minus 13 centimeter, and in femtometer it is 1.2 suppose, right, most probably. Okay, so if you put that only here, this type of problem we have done several times, and again they are giving the same problems. I don't know why. Minus 3 and it will be 1, so it will give you 550 keV roughly. Oh, the unit is semi here, so semi it will be keV, 550 keV. And now you have to calculate your thermal energy with that Coulomb potential, Coulomb barrier. So you can see that in this problem you don't need any understanding of the non-resonant reaction or resonant reaction or anything else. Just it is coming, it is directly asked from the first or second weeks of material. So this kT is K is kV, that is a Boltzmann constant, is actually equals to 550 kV. If you do it and put that kV in proper unit, that means in electron volt unit, I have asked you to remember that. So it is 550, sorry, it is 550 keV means 550 into 10 to the power 3 eV, kilo means 10 to the power 3, and kV is 8.62 times 10 to the power minus 5 in terms of this unit. So please try to remember it. Okay, and it will be 6.38 times 10 to the power 9. This unit will be there, EV will be cancelled out. So okay, right. So it is the temperature which is required, and as it has been expressed as Tn, so we write as T9 as 6.38, because T9 is T divided by 10 to the power 9 K. So 6.38 roughly 6.4, that is the answer. T9 equals to 6.4. This energy we must have to overcome the potential barrier, Coulomb potential barrier for protons. For other elements the change will only be in Z1, Z2 and A1, A2. All the process will be same, exactly same. Okay. Now coming to the second problem, which nuclear reaction is responsible? Okay, that I will do. This I will do. I will just now go through the problems which can be done from the previous week's material. So at the energy 1 keV, that means T9, okay, the order of the tunneling probability, okay, so the tunneling probability is actually e to the power minus beta by root over E, which I have written repeatedly, that is similarly as e to the power minus 2 pi eta, which has been used by sir. So this has been used by sir and this has been used by me, no difference, this is exactly equivalent. Right? So and if you go through that material of week 4, I think, so 2 pi n, it can be written as, it is exactly similar as this, right? 2 pi n is 31.29 times Z1 Z2 mu in AMU unit divided by E in KEV unit and root over that. So if you do it, just try to remember this, otherwise you cannot do it. You can, you have to do it from the base equation, which is very time consuming. Okay, and one thing, 0. E in keV, so Z1 Z2 mu, and if you calculate the energy, oh, you don't have to calculate, it is given 1 keV, what I was trying to find it, 1. Okay, so it is in keV unit, and the other thing was in AMU unit, because mu is m1 m2 by m1 plus m2, and if you put proton for proton, it is 1, both m1 and m2, then you will get 0.5. so the answer will be 22.125, and this is the value of 2 pi eta, not e to the power minus 2 pi eta, but the probability is proportional to e to the power minus 2 pi eta. So the probability is proportional to e to the power minus 22.125. Okay. So that is 2.46 into 10 to the power minus 10. So this is the probability of tunneling of proton-proton reaction. So in question number 1 we have done same type of problem, but using the classical treatment, classically, because all the Coulomb energy and everything, but here we are doing it in the tunneling probability, that means we are in the quantum domain. Okay. So 2.46 10 to the power minus 10. So this will be the answer, I think. 2.10 to the power minus 10. They have not considered the factor first here, I mean first factor here. Okay. So this is a good problem 5, for which you need to understand the resonance and non-resonance reaction. Okay. So what we will do, so here we have to find the energy the resonance energy are given as 10 kV, 30 kV, 50 kV and 100 kV. Okay. Okay, and the temperature is given as 0.02 gigakelvin, and for this particular reaction, this reaction, that is 20 Ne plus proton equals to 21 sodium plus a gamma. So we have to calculate for which energy the reaction will occur. Okay, so and other thing is given is the resonant energy are given. So 10 kV, 30 kV. Okay, so these 4 values are given, 4 options are given, and we have to find out for which energy value the reaction will happen. Okay, now we will do it. Okay, so first, I don't have this question is okay, I will do it other way. So first we will find the gamma peak. So one thing, one question I have regarding this particular problem, so by how they have solved the problem is actually considering the gamma peak and the gamma width. Okay, but I don't understand this is, if any of you can understand, just tell me, just then why they have given the value of gamma, I mean omega gamma, and this condition I don't understand. I am telling you the truth, I don't understand for why they are given this particular data for that problem, because they want me to do the problem by using the gamma peak. That means they are considering the non-resonance reaction only, but why these values are given, I don't know. Okay, so that is the problem I faced, I mean that is the issue I faced with this particular problem. I will try to go through the NPTEL committee why they want to do it like this way, but I will do it anyway. So we will do it in the gamma peak and gamma width that way. Okay, so gamma peak E0 for a problem for a reaction can be written as Z1 square Z2 square mu T6 square 1/3. This I have done, I mean in the last class. So for our case 1.2, for 20 Ne, 20 is the mass number, the atomic number is 10. Okay, 10 square, and proton is 1. Okay, and the mu T6 square 1/3 will be there. So T is given as 0.02 gigakelvin. 0.02 gigakelvin means 9 Kelvin. That means 2 into 10 to the power 7. Yes, 2 into 10 to the power 7 million Kelvin. 2 into 10 to the power 7 Kelvin, sorry, and which is equals to 20 million Kelvin. So from gigakelvin we have just converted it in million Kelvin, because that is important, because we have to put the T6 in terms of million Kelvin, because this expression demands that T6, you can see. So T equals to 20 million Kelvin means T6 equals to 20. So as the expression demands the T6, we have converted our T to T6. Okay, now and mu is actually M1 M2 by M1 plus M2. So for our problem for neon it is 20, it is 1, 20 plus 1, that is 0.95. Okay, just we will put this mu and this T6 in this expression, which will give, so I don't have much, I will put here, I will erase something if needed. So E0 is 1.2 100, 1, I will not write it, mu is 0.95, and T6 is 20, right. So this will give you a value of 38, I mean 1.5 1.2 times 32.45 keV. That means roughly 40 keV you can say, or to be precisely 38 point something it will be, roughly 40 keV we are using. So it is the E0. Now you know this gamma peak, if it is a gamma peak, if it is E0, the and if it is delta, the reaction will mainly happen if the energy of the particle is from E0 minus delta by 2 to E0 plus delta by 2, right. This is the energy window of the energy for which the reaction will happen. Now E0 we have calculated, so we need delta right now. I will come to this part, no problem. So delta is 0.749. All this expression I hope you can write it directly, because it is been 2 or 3 weeks that you have taught these equations. And if again we put 10 square 100, mu is 0.95, T6 is 20, 16. Okay, that will give you delta as 17.05, or roughly you can say 17 kV roughly. So we have E0, we have delta. Now the energy window will be E0 minus delta by 2, that means 40 minus 17 by 2 to 40 plus 17 by 2. Okay, so this will give you 31, it will give you 48.5 kV. 17 by 2 is 8.5 roughly, roughly no, it is 8.5, and it is 31.5 kV. So this is the energy window. If your projectile particle energy, I mean energy of the projectile particle is in this range, okay, so if this holds, then the reaction will occur. Okay, so roughly 30 to 50, very roughly 30 to 50, if it is between that, your reaction will occur. And the options it is given as the energies are 10, 30, 50 and 100. Yes, so this 30 and 50 is in the range of the E0 minus delta by 2 to E0 plus delta by 2. So the answer will be that if your resonance energy is 30 to 50 keV, then the reaction will occur. For 10 is much lower than the energy range, and 100 is much higher than the energy range, I mean the width of the gamma peak. That's why for those two value the reaction will not occur. So that is the result, ER 30 to 50 keV, exactly coming from this, I mean range. Okay. So yes. Just a second. Okay, so I think they are comparing something in this problem. That's how they have formulated this problem. If this reaction happens non-resonant way, then what will be the gamma peak? And that's why I think they have used that hypothetical term. And hypothetically, they are considering it is also happening in the resonant way. So, and given that if the particle has this type of resonant energy, what will be the range of the energy for which the reaction will happen? I think that's why they have, that's the way they have they tried to formulate this particular problem. But this is a confusing type of problems. I don't know why they have given this thing. Okay, so this was the result. Now this was 5th and 6th problem. 6th problem, it is also a good problem. So I am erasing this particular thing, okay, because I don't have space. I forgot to add one more page between those problems. Okay, so consider a resonance state of 1.4 MeV resonance state in the reaction. So that means this is a resonance reaction. At energy is also given, temperature also given. The measurement results in a resonance state of 1.3 MeV by mistake. Okay, so the actual value is 1.4 MeV, but by mistake someone has calculated this as 1.3 MeV. Then the factor by which the resulting narrow resonance reaction rate will be high. Reaction rate, whenever you see reaction rate, just remember this quantity. This tells you the reaction rate actually, with other N1, N2 also, but this is the main thing. N1, N2 are just numbers. Okay, so we have to compare sigma V for 1.4 MeV and sigma V for 1.3 MeV. That we have to calculate and we have to compare. So this is theoretical, this is experimental, according to the problem what it says. Okay, so as I have shown you, the sigma V for non-resonance reaction can be written as, I have not derived it, but I have just written it, h cut square gamma omega e to the power minus ER by KT and F. This is the sigma expression of sigma V for resonance reaction. Now we will calculate sigma V theoretical, like TH. So it will be experimental, I will write, because I have to calculate the change also, and sigma TH. Okay, so it will be the 2 pi by mu KT h square gamma omega, all will be cancelled out from the numerator and the denominator. That's why I am not writing it. The main change will be here. It will be e to the ER, what is found experimentally by KT, and here it will be e to the power minus ER theoretically by KT, right? It will be the sole thing. All the other terms which are associated with pi, mu, h square, gamma, omega will be cancelled out. Those terms will be cancelled out. That's why I have not written it. So it can be written down as e to the power R TH minus e to the power ER, not e to the power experimental by KT. So this is the factor by which the resulting narrow resonance reaction rate will be high, because of the error in the calculation of resonance energy. So it will be e to the power 1.4 minus 1.3 MeV. That's why we convert it in keV, and K again we will write it in unit which we have used earlier. So it will be 0.086 into 2.5 into 10 to the power 3. Just don't focus much on the values which I am writing. You have to just understand the process, how to do the problems. Those values can be anything arbitrary. Okay, so it is the process of doing that. So the value will be 1.59. So your sigma experimental, which is due to the mistake of the resonance energy, that will be 1.59 times higher than the resonance rate, which can be calculated by theoretical understanding of the reaction. Okay, so it was the answer, 1.59. Yes. Now 7, this problem I have done in assignment 3, I think. Just go to that, yes, and it is a direct problem from the material which sir has covered. Okay, so that you can do, otherwise I will do it. But one thing I want to do, that is the 9 problem number 9. Yes, calculate the mean lifetime of a deuterium. So you can see here we have to calculate the mean lifetime. So mean lifetime is again is from week 4, not related to week 5, week 3 I think, not related to week 5. So mean lifetime, all this expression we have done. Mean lifetime tau p, it is rho xh by mh, because we are considering the I should have told it, that proton, deuterium plus proton 3He plus gamma, this reaction we are considering. So Na and sigma V for this proton deuterium reaction, to the power minus 1. Okay, now if you put the values which is given, rho 100, gram per cc. X age is 0.5. M age is actually 1 point, for proton it is 1.67 into 10 to the power minus 24 gram per gram, and Na sigma v, the whole value of Na sigma v is given, that is 1.01 10 to the power minus 2 semi cube mole inverse, second inverse and whole inverse. And if you want to convert your mole to the number of particles, because at last we want our result in terms of unit of time, that means this semi cube will be cancelled out by this semi cube, gram per semi cube, this gram. So, mole inverse, second inverse will be there. Now, we will convert our mole inverse to a number, so that we at last we get the unit of second. Okay. So, 100 into 0.5, all these things are there, 1.01 10 to the power minus 2, just I will write the mole inverse as number of particles in a mole is 6.023 into 10 to the power 23, right? And the unit will be, so second inverse will come out with another inverse, that will be second inverse is second, and if you calculate it will be 1.99 second, or roughly 2 seconds you can say. So, the whole thing lies in the remembering of this particular formula. If you can remember this formula, you can do it directly and it will not take more than 2 to 3 minutes. So, 2 seconds is the answer, the mean lifetime of this particular reaction, deuterium plus proton. And you know, after doing the 5th week class, that it is a very important reaction in the proton chain. Okay. So, this was the problem. Now, all the other problems are related to the hydrogen burning, I mean nuclear fuel burning. So, I will just give you a brief overview on nuclear burning, and then we will do those problems. Okay. And one thing I don't, next day, I mean next week I will consider a small part of the neutron induced reaction. Till now there is no problem on this particular topic, the neutron induced reaction. So, for now I am just bypassing this particular topic, but if needed I will do it in the next class. Okay. Now, let us go to that thing, that hydrogen burning, I mean the nuclear burning. So, you can see that Vc, which I have written repeatedly, Z1 Z2 square by R, which is the Coulomb potential for two particular element of Z1 proton number and Z2 proton number, and it will be the Coulomb barrier if the overcome or the tunneling can overcome, if the tunneling or can overcome this Coulomb barrier, I mean the probability of tunneling, then the reaction occurs. Now, this Vc is directly proportional to Z1 and it is directly proportional to Z2. So, if your Z1 and Z2 are small numbers, then the value of Vc will be small. If your Z1 Z2 is higher, then the value of Vc will be higher. So, why I am telling this, because instead of proton, if you consider iron connection, I mean Coulomb barrier. So, for iron Z1 Z2 will be 26 and the Coulomb barrier will be much higher. So, with increasing value of A or increasing value of proton number, whatever, these two are equivalent, your Vc increases. That is why the starting point of nuclear fuel burning is the hydrogen burning, because hydrogen has the less Coulomb energy, and Kt is Vc, which I have done for the first assignment problem. If you equal Kt with Vc, that will give you the temperature required for overcoming the Coulomb barrier, and if your Vc is higher, then you need a higher temperature also. So, your temperature needed for the reaction to happen is also higher. So, for lower value of temperature and for lower value of Coulomb barrier, the proton reaction mainly start to happen, and with time other reaction, other nuclear burning of other higher order elements comes into the into the picture. It happens in the start, but it starts with the hydrogen burning. Okay. So, hydrogen burning is the starting point. Yes. Now, hydrogen burning, the overall process is quite difficult and it has 2 or 3 sub steps, but the overall picture is 4 protons. This is not a reaction, this is I am just writing. 4 protons will react and it will make it will make a helium. Well, this is the total picture, that 4 protons will react and 1 helium nucleus will be formed, and the Q value of this total process, which is a combination of 2-3 process, is 26.731 MeV. Okay. Now, it will happen through different process. So, that is, first there are 2 proton, it will react and it will make 1 deuteron and 1 positron and a neutrino will be there always. The reaction of the Q value of this particular reaction is 1.44 MeV. So, in this reaction the deuterium forms. Okay. So, the deuterium has formed, just a second. Yes, this has been done. So, the deuterium has been formed. Now, what will happen? This deuterium will react with another proton. So, here other reaction can also happen, but right now I am just writing the predominant steps of this reaction. Proton can react with deuterium, similarly deuterium also can react with other deuterium. So, I will write those prominent reaction which is happens say 85% or 15% can be other type of reaction. So, P plus D, it is the helium will be formed and the neutron, very sorry. So, it will form 3 He helium plus gamma, and Q value of this is 5.5 MeV. These are steps. Okay, this is the first step of hydrogen burning, this is the second step. So, another thing can happen for this second step, that 2 deuterium can also react and that can give a neutron which has Q of 3.27 MeV. This can also happen. So, first step proton which give you deuteron, then deuteron with proton or deuteron with another deuteron will give you 3 He. This is the second step, and at the third step, this the 3 He has been formed. This 3 He can react with another deuterium, because deuterium is there, because it has been formed in the first equation itself. So, there will be a deuterium at the surroundings of the helium, 3 He helium, and it will give you, it can give you 5 Li plus gamma, and Li will again decay. So, we are not bothered about, because it is 14% reaction will be happen through this process, but the main dominant part will be this 3 He. This helium will react with another helium, that will give you 4 helium and 2 protons. This will occur 86%. Okay, and Q value of this total, this 2 different thing also have some Q value that I have forgot, but this 1 plus 2 plus 3 is actually the total PP chain or hydrogen burning, and the total Q value of this PP chain by combining this 1.44, this 5.5, and there will be other Q values also, that will give you the 26.731 MeV. So, this is the total Q value of these 3 different process by combining all the process. But the main point is, we have started with protons. So, yes, we have started with protons and we are getting helium. Okay, so this is the important point, that we are getting the helium. Now, okay, yes. Now, yes. So, you can say that you have told that 4 protons, here only 2 protons, but here 2 protons will made a deuteron, and here also 2 deuteron, that means 4 protons are taking part into the reaction. That is why we call that 4 protons is taking part into the reaction, and we are getting a helium atom. Okay. So, so these are the main dominating reaction. This is the general understanding of helium burning in the star, And now we will calculate, because there is some question depending on that, that how much times the hydrogen burning will occur in the star. Okay. So let us start that hydrogen burning. Okay. So this first step is called the hydrogen burning, main step of hydrogen burning, because it takes a lot. I mean, I will not write it. So the first step, it is the main part of hydrogen burning, because it is a weak reaction, that I can write. It is a weak reaction, and weak reaction generally occurs in a very long time. So the main time of hydrogen burning phase are coming from the proton reaction, because it is a weak reaction. All the other reaction are strong reaction, they will occur quickly, but the weak reaction, the first step, will occur very slowly. Now we will calculate the time scale of that proton reaction, which will create a deuteron. Okay. So just considering proton reaction, the first step, which is giving the deuteron. I am not writing the electron and neutrino here. Okay. So if you calculate, no one, so okay, let me write this is the first step. Now the Q value for this particular I have written is 1.44 MeV. Now this 1.44 MeV, sum of the energy of this Q value will be taken by the positron and I mean neutrino. So if we calculate, I mean, due to the annihilation of the positron, because positron can not be in a free state, it will react with the electron, and there will be annihilation of the positron. That annihilation is included, the energy of the annihilation is included in the 1.44 MeV. If we just subtract that annihilation part, then that will be, the Q value will be 0.42 MeV. So this much energy is available for the positron and that neutrino, these two elements, to take away. So they can take away energy of 0.42 MeV, combined energy of 0.42 MeV. And if you calculate, you can see the spectra also. I have proposed that it will follow this type of spectra, that neutrino and positron. There will be peak at some 0.26 MeV, I think. I may be wrong, just go through the class. So 0.26 MeV for neutrino, and same there will be some positron, so I will not write it. But the main point is, this much energy will be taken away by electron and neutrino. Okay. This is the kinetic energy of that two elements. Taken away means this will be kinetic energy. Now the rate, if you calculate, it has been calculated, the rate of this reaction sigma v pp is actually 10 to the power minus 43 centimeter cube second inverse. It has been measured at T6 equals to 0, because when we are telling the rate of something, we must specify the temperature, because that is the variable in the expression of sigma v. Okay. Now if you consider that your hydrogen production is 0, your XA is that the hydrogen fraction is 0.5, rho is 100 gram per cc. If you consider this type, this is the typical value for a sun, so mean lifetime of this reaction, this PP reaction, can be calculated, which is 1 by NH sigma v. It is from third week's material. And if you put everything and calculate, I have shown you how to calculate this mean lifetime just few times before in the problem, in one of the assignment problem. And if you can calculate, it will be 10 to the power 10 year. Okay. So the mean lifetime of this particular reaction is 10 to the power 10 year, which is a very large, I mean long time scale. So that's why the stars consumes the nuclear fuel very slowly, because this particular reaction is the starting of nuclear fuel burning, and if the starting stage is taking 10 to the power 10 years, so the other reaction will happen after this first step. So it is the reason why most of the burning time, the total burning time, is dominated by the proton reaction. Okay. So you can find there is a question in the assignment where, yeah, So, which nuclear reaction is responsible for a very long time of the sun? So, the very long time is coming because of the proton proton reaction, this one p plus p, which is giving you a deuteron, electron, it should be positron I think, and the neutrino. Okay, so this is the main reaction, and this is taking the higher time, that is 10 to the power 10 year. Okay. Now, how much hydrogen in the sun is involved in the hydrogen binding process? This will also come in few minutes. So, I have told you that hydrogen binding has started. It is taking it takes a very long time. That's okay. And this is the 3 steps, 3 dominating steps. Other reaction can also be happen, but these are the dominating. That, as I told you, this reaction is 86% mainly. Okay, so this is the formation of helium to hydrogen. Now, it was just a second. So, okay, so yes, now what I will do, that first step we have done, that proton proton. Now we will consider the deuteron deuteron reaction, this reaction mainly, or the proton deuteron reaction. These two reaction we will see, that proton plus deuteron, the second step it was right, that is 3He plus gamma, or deuteron plus deuteron, that can be 3He plus neutron. Now the Q values are the Q values are already written. Okay, so this is the thing. Now from here we can calculate the number of deuteron with respect to proton or with respect to hydrogen. Proton means we are considering hydrogen. Okay. So the change of deuteron, d capital D means deuteron. Okay. D, because if I write both small d, that will be dd, small dd, that is not good way. So capital D means deuterium, and it number will depend on the two factor, the rate at which it is getting produced and the rate at which it is getting destroyed, because from p plus p it is getting produced, and from by these two reaction it is getting destroyed. Okay. So that's why the production rate for from pp reaction, which was the first step, and the destruction rate, and we are considering this pd reaction. You can consider this dd also, no problem in that. I am considering this p plus d reaction because it is I mean these two reaction are most dominating of the other of the 5 reaction. Generally in second step there is mostly 5 to 6 reaction can happen, but these two are predominant reactions. So if you calculate is R rate, I have told you that N1 N2 sigma V is the rate every time, rate of 1 2. So for proton it will be proton number density, that is H. We are denoting the number density by the alphabet H for hydrogen, capital D for deuteron. So and it is, and 1 plus delta factor will be there because proton proton is both are similar, same. So the delta factor comes here, and sigma V proton proton minus number density of protons, number density of deuterons, sigma V PD. PD reaction. And for equilibrium, not equilibrium, quasi equilibrium, it is a state when we assume that the chemical change of the sun is in a chemical change or formation of chemical is in a equilibrium state. Okay, so this is a quasi, it is not in in the state, the chemical composition of a particular star is not in equilibrium at any time, but we are considering that for some moment there should be some degrees of equilibrium. That's why we called it a quasi equilibrium, and it is possible only when d dt is 0. That means there is no production of deuterons, no production of no destruction of deuterons. That will give you a constant number equilibrium. So if you do it, then you can just put it here, then you can find that your d by h, this is the number density of deuteron by protons, is sigma v pp by sigma v pd 2. And if you calculate that sigma v pp, we have calculated many times, and sigma v pd also we have calculated, I think, in the assignment problems, and it is very less than 1. That means your deuteron produce deuterium, the number of number density or number of deuterium will be very small than the number of hydrogen. If there is suppose 1000 particles of hydrogen, then there will be 1 deuterium, this type of thing. Roughly I am saying it, this is not exact value because this is very less than 1. Okay. So, deuterium burning happens in this way. Now, we go to the third reaction, third step. What was the third step? The 2 helium, 86% we will consider this particular channel. So, 86% 3, it is the helium burning, and this was the deuterium burning, and the first one was the hydrogen burning. Okay. So, the reaction was 3He plus 3He 4He plus 2P. So, this what I have done here, this you can do it also for this reaction, no problem in that. I have just focused on particular reaction to give you the idea, and here in third step it is the main dominating 86%, that is why we are not considering the other reactions. Now, if here also you write the projection rate of 3He, so d of 3He by dt, it is the rate of projection, that means rate of projection is proton deuterium. So, now for stage 3 this reaction is the projection reaction, that means Pd minus, and this is the destruction reaction R3He 3He. Okay. So, it can be written as like this, sigma V Pd I am writing as 1 2, because it is easier to follow this, otherwise I have to write 3He again. So, 1 means proton, 2 means deuteron, minus 2 3He, and the delta factor sigma V 33. Sigma V 33 means sigma V of this particular reaction. So, if you can, so this is the equation. Now, from this expression which we have calculated for the second step, the earlier step of the third step. So, D can be expressed in terms of H, right? D will be H sigma V Pp by 2 sigma V Pd, right? I can write this way. So, we will just put that instead of D, H is there, and H sigma V Pp by 2 sigma V Pd sigma V 1 2. So, sigma V 1 2 and sigma V Pd are same, because I am writing 1 for proton, 2 for deuterium. This will be cancelled out. Okay. And 3He sigma V 33, it is there. So, the final expression will be H square by 2 sigma V proton I am writing as 1 1 minus 3He square sigma V 33. Okay. So, what I have done, I have just written down the projection rate of deuteron and the projection rate of 3He and the destruction rate of 3He, and I have just replaced my number density of deuteron in terms of number density of protons, which has been calculated in the previous cycle, I mean previous step 2. Okay, that we have done. And again, if you consider a quasi equilibrium, as we are interested in that part, quasi equilibrium, then d 3He by dt equals to 0, that means your projection rate is same as the destruction rate, and that will give, just put the d 3He by dt here, which will give you 3He by H number is actually sigma V 1 1 by 2 sigma V 3 3. Okay. So, by this you can calculate. So, if you have been given some problems where the reaction rates are given and you have to ask to calculate. So, do not consider this 3 as any value. Okay. You have been asked to calculate the number density. You can calculate by this way. If multiple steps are involved in that particular chain of reaction, that can also be done by this particular formalism. Okay. So, that has been done, and now one thing I have not written. Okay. So, yeah. So, this another question there is, that is the theoretical question. I will just tell you that it is done, 2 is done. 3 is how much of hydrogen in the sun is involved in the hydrogen burning process. So, if you calculate roughly, it will be 10%. 10% of the sun is involved in hydrogen burning process. This has been calculated. Okay, this is for you. It is a theoretical question because we cannot calculate it from our known expression. We can get some idea, rough idea, which I will tell you, but not exactly. So, where is that thing? One, just a second. Yes, okay. Just roughly I will tell you why we consider it as 10%, because so up to this point we have just completed the PP chain, which is the hydrogen burning, then the deuterium burning, then the helium burning, and in the overall process 4 protons are creating a helium nuclei. I have not gone to CNO cycle yet, that I will go in the next class, because first reaction we have done for up to helium. Okay, now okay, so as we have seen and we have calculated the mean lifetime. So, mean lifetime for proton proton reaction is actually mean lifetime, no sorry, is actually 10 to the power 10 years. So, this is a very high, very large value of time, and most of the time the star will burn is proton. Okay. So, and the Q value of the total PP chain from proton to helium is actually 26.73 MeV, the Q value which I have written earlier. And as I told you that average energy of neutrino which processed in this particular reaction is 0.26 MeV or 260 keV, you can say. Okay. Now, the loss, because with that energy the neutrino will escape, it will not contribute in the energy projection of the sun. It has been repeated in several times in the class. So, total loss is 26.73 minus 0.53, because 2 neutrino will be 2 thing will be go there, that is why 26.2 MeV. This is just some approximate calculation to give you the idea of 10%. Why 10% we consider? It is a consideration. And the luminosity of the sun, yes, and the luminosity of the sun is actually 2.4 times 10 to the power 39 MeV per second is a luminosity. Now, if you calculate the rate of fusion, rate of PP fusion, that can be calculated as it is, I have done it, yes, the rate N is L by 26.2 MeV, because in every reaction 26.2 MeV energy is liberated, and you have a total energy contribution of 2.4 times 10 to the power 39. Now, if you just divide it, you will get the value, which is, I will write 10 to the power 38. So, 10 to the power 30 reaction of proton is happening in sun per second. Okay. And if you calculate the mass, it will be roughly 616 ton. So, 616 million ton, sorry. Yeah, I was also surprised what I am writing. So, 6.6 million tons is burning in a single second, and the total mass of the sun is actually 2 into 10 to the power 30 kg. So, you have the total mass, you have the mass, rate of mass at which the PP fusion is happening. Now, if you calculate that how much time that reaction will occur. So, how much time it will take to burn all the mass of the sun. So, that time will be given by mass of sun divided by 616 million tons. You just convert tons to the kg, which is given here, and you will find it, the value is let me write it, 10 to the power 11 here. Okay. But this 10 to the power 11 year is very high, because we have already seen that mean lifetime of proton-proton reaction is 10 to the power 10 years. But by considering, if we consider the total mass of sun is actually hydrogen, and that burning is happening, then we are getting a age which is 10 to the power 11 year, that is greater than the 10 to the power 10 year. So it is not consistent, because your reaction is happening 10 to the power 10 year, and the reaction lifetime means that is the lifetime of the star. So there is some problem, I mean some issue in understanding. So this is not possible that the whole mass is in hydrogen burning stage. Now if we consider the 10% of total mass in hydrogen burning state is going to PP reaction, that means 10% of the total mass is in hydrogen, then this will decrease by 10%. That will be, it will be, now if we consider 10%, that means 0.1 m mass by 616 million tons, that will give you a rough of 10 to the power 10 year, which is consistent with the burning lifetime. So the lifetime we are calculating from the burning from the nuclear burning rate, which is here mean lifetime of the reaction, and another lifetime we have calculated by using the liberated energy for each PP chain and dividing the total luminosity by that each liberating energy. So two lifetime, there is, this is the two, I mean different way of calculating the lifetime. And if we only consider the 10% of this total mass is going to the PP fusion reaction, then only these values are consistent. That's why we generally consider that 10% of the total mass of hydrogen, total mass of sun is in hydrogen state, and which is going to the helium, just to match the two lifetime which has been calculated in different way. So that's why in this question, how much of hydrogen in the sun is involved in the hydrogen burning process? Only 10% of the hydrogen is involved in the hydrogen burning process, otherwise the lifetime could not be matched. Okay, so that is the rough understanding of 10%. So okay, this as I told you, this I have already done in third class, just go to it. And the last problem, it will take just 2 minutes, not more than 2 minutes. Just the values, I will not do it also, I will just tell you what to do. Yeah, so this number 8 problem, it is the 7 lithium nucleus is bombarded with protons. That means your 7 lithium nucleus is bombarded with protons, and that will create alpha particles. So it will create 2 Ag4, that is alpha particles, and the number of particles will be 2 alpha particles it will create. And calculate the kinetic energy of each of the alpha particles. Okay, that means you have to calculate the energy released, that is mass of 7 Li plus mass of protons minus 2 into, as there are 2 particles, alpha particles, it is alpha, right, 2 alpha particles times c square. So just put this MP in AMU unit, this M alpha and M lithium all in AMU unit, and the c square, and use that, I mean all will be in AMU unit, I will not write, just put those values into 931.5 MeV. This will be your energy released, that is 17.35 MeV, you will get that result. Okay, just put these values here. And as 2 alpha particles is created, this energy will be divided by 2 particles. So each alpha will take half of the energy. Each alpha particle will take 17.35 by 2 MeV, that is roughly 8.67 MeV energy. Okay. So 8.67 MeV. This was the question of 8. So I think I have covered all the material which I wanted to do today. Just one thing I have not considered, that is the neutron induced reaction. So I will cover it in the next class. It will take only 15 to 20 minutes at max, and I will give you the, by doing this tutorial we are just brushing up the theoretical understanding which we have learnt in SARS class. So this is the purpose of this tutorial, not only solving the assignments. Assignment solving is a part, but we are also brushing up our knowledge which we have understood. Okay, so if any of you have any question, you can ask, otherwise we will end today. So if you have question, please ask. It is already 8. Yeah. And that book, as I have told you, I will try to take the photo of those pages if it is available in the library, because in my institute the library is very rich. I should find it. I mean, it is possible to find it there, and I will give that to you guys. Okay. So if anyone have question? Okay. So otherwise we can end this meeting. I mean, we can end this class today, and we will meet next week same time, Tuesday 6 p.m. Okay. So thank you for joining, and I am ending this.